Sampling Methods, Mass Analyzers, and Detectors Training Video by Monica Gamez. Table of Contents. Sampling Techniques. We'll start with a solid phase extraction, also known as an SPE. The extraction is done with a solid material that selectively retains compounds. The liquid sample is then passed through an SPE cartridge. Unwanted components are then removed via washing, and remaining analytes go through an elution solvent to be collected. Analytes are then analyzed by a chromatographic instrument. Some pros of this type of sampling technique is it allows for different sorbent materials, which can make the process more selective for specific analytes. It also allows for concentration of analytes and can be applied to a wide range of samples. Our next sampling technique is known as solid phase microextraction, SPME. A fiber is coated and then exposed to the sample. The analytes are then absorbed into the coating. Once extraction is complete, the sample may be introduced to the chromatographic instrument. This sampling technique pairs easily with gas chromatography or high-performance liquid chromatography. Some pros: less solvent is needed. It increases the extraction speed, and it works well with both of these chromatographies that I've stated. It also can be used for volatile and semi-volatile compounds, and it has been used in the past to determine alcohol concentration in blood and pharmaceutical analysis. Mass analyzers. They are used to separate ions produced during the ionization stage via the mass-to-charge ratio, also known as M/Z. The first analyzer we'll be looking at is the quadruple mass analyzer, which contains 4 circular rods parallel to each other, which selectively filter ions based on their mass-to-charge ratio using varying electric voltage. Now, by applying varying voltage to the rods, only ions with specific mass-to-charge ratio pass through the quadruple at any given moment. The second analyzer we'll be talking about is the time-of-flight mass analyzer. So this does not use an electric or magnetic field, and separation is based on the movement and velocity of the ions. It is called time of flight due to it being named for the time it takes for an ion to travel the length of the tube being analyzed. At higher masses, resolution is lost, and therefore a reflection must be added to the analyzer. Moving on to detectors. So detectors are used to identify and quantify the analytes. They collect the data and convert it into an electrical signal, which is then read by a computer. So the first detector we'll be talking about is a UV visible detector used to detect and quantify substances based on their absorption of light. This is commonly used for liquid chromatography or high-performance liquid chromatography. So this detector detects and quantifies the substances based on how they absorb light, either visible or ultraviolet. It is very useful for analyzing drugs, dyes, and other organic compounds. The second detector we'll be talking about is the fluorescence detector. It is used to detect and quantify substances based on the substance's ability to emit fluorescence. It is commonly used in high-performance liquid chromatography or thin-layer chromatography. So it is useful when analyzing substances with natural fluorescence or substances that have been tagged with a fluorescent marker, such as drugs, biological substances such as blood and urine, or certain dyes. Some common chromatography methods are gas chromatography, which is commonly used for the analysis of volatile compounds such as drugs, accelerants, and explosives. Liquid chromatography mass spectrometry, LCMS, used for the identification and quantification of compounds such as drugs of abuse, pharmaceuticals, poisons, toxins, gunshot residue, and several others. And the last one, high-performance liquid chromatography, HPLC, which is used for a wide variety of compounds, including drugs, toxins, and biological samples. So this is an example of a simple diagram of gas chromatography, while the second picture is an example of high-performance liquid chromatography. Some specific examples. So gas chromatography using a solid phase extraction, a quadruple mass analyzer, and a UV visible detector would be suited to analyze drugs such as pharmaceuticals, illicit drugs, or prescription medication, toxins in blood, urine, hair, or tissue samples, fire debris such as residue from fire scenes or accelerants, and explosives such as residue from explosive devices. Other chemicals, such as trace analysis of organic compounds and various material, can also be analyzed using these specific methods. Another specific example is using high-performance liquid chromatography with a solid phase microextraction, a time-of-flight mass analyzer, and a fluorescence detector. So this method would be suited to analyze the following: drugs such as pharmaceuticals, illicit drugs, and prescription medication, toxins in blood, urine, or tissue samples, arson evidence such as residue from a fire scene, explosive detection such as residue from an explosive device, or other forensic analysis such as profiling and identification of metabolites and biological samples. As you can see, most chromatography instruments do overlap and can test the same types of materials, just at different quantifications and at different sensitivities. So attached, please find my references